Okay, good morning. Nicole, there's only one person here, but that's okay. This is all being recorded, so that's you can watch this offline. All right, so today we begin Module 9. This week we will cover Module 9, and Module 9 is where we go over the material that is in Chapter 9. Now, because this week is flex week, or it has flex day in it, we only have today as a day that we have this Zoom session. Thursday will be flex day, so we don't have any lab activity this week. So here, let's have a look and see what we have. All right, let's see what we got over here. All right, so you see, this is our very nice Canvas shell. And so you go to the modules area, and now we are here. No, sorry, we're here. So we're doing module 9, and this is statics and torque. Now, so this is week 9. So this means that actually we are a little bit more than halfway through the course. So well done. You made it. Well, you made it this far. So this is very good. All right. So let's see. So what do we have for you in this module? So statics and torque has to do with the physics of things that are just static. So what do I mean by static? What I mean is they ain't moving with respect to the ground. All right. And so why is this interesting? Why is this important? This is important because if you can understand the static equilibrium of a system that you have constructed, then you can predict, is it going to collapse or is it going to remain stable? Okay, so people who build bridges or, do stuff like that, they have this cool video in the book. Here, I'll show you real quick. Oh no, wait. Oh no, that's not the one. Okay, I gotta find it. They have this cool video in the book where they, actually, you know what, I can show you. Yeah, see here. Okay, so you see if we go to this guy, there we go. And then we go to the introduction. Oops, we go over here. Yeah, you can see it. All right. Come on, statics and torque. All right. So you see, they have this cool video here where you see the cheerleaders, right? So what does this have to do with cheerleading? Well, you see the cheerleaders, they have to jump up on top of each other, and then they have to like maintain a pose, but while they're on top of each other. So the question is, what have you done? Well, you have constructed a structure, right? It's called a human pyramid. And so you build a structure by placing people on top of each other. And then, if you can attain static equilibrium, then the structure will not collapse, right? So that's why that's interesting. All right. So as usual, what I've done is I've placed the relevant sections of the text over here, and together with the video summary, which I borrowed from a fellow named Fancy Physics. who's on YouTube. So you can watch this video. It's actually pretty short, but I think he does a good job of summarizing the main points. So you almost don't even really have to read this if you just watch the video. I think that kind of gives you what you need. And then once you have sort of gotten through this, there's a part at the end, toward the end, where they've got a discussion of simple machines, right? So simple machines are things that that provide a mechanical advantage. All right, they provide a mechanical advantage. So what does that mean? Is that you can, you know, they, in a way, they amplify a force, right? Some people call it a mechanical amplifier. So like you apply a small force, but you can generate a very large effect by using a simple machine. Yeah, we'll talk a little bit about that more in a moment. But basically, once you've seen this section of simple machines, then you should be able to participate in the discussion. And so for the discussion this week, what we have is we have you trying to create a simple machine using the pulleys that are in your lab kit. All right, so you see I have an example here. What you're going to do is you're going to take an object that you can hang from the hook of your spring balance, and you want it to be, you know, maybe 4 newtons or something. And then what you want to do is then you want to lift it using a simple machine, and you want to show that actually you can lift it with less force than you would use to lift it directly. Because what the simple machine does is it provides a mechanical advantage. Okay, so you're going to try this out and you know, post some pictures. All right, so that's how that works. Okay, so again, there's no lab activity. So then all you have is your homework set, and you've got your quiz. Okay, and then that pretty much wraps it up for this module. I think there's a module wrap up section at the end. Here, I don't know. Let's see. Yeah. Oh, it looks like some people have already started answering. Okay, that's very good. People have started answering. Okay, there's your quiz. And then let's see. Oh, you got your optional practice problems. There's only a handful. Okay, there, yeah. And then you've got your short module wrap up. And then that's it. Then we move on to module 10. Okay. So are there any questions about what we're doing this week before I actually get into explaining some of the physics? All right. Okay, so what we are going to do now is we are going to take a look at the physics of the statics and the torque. So this is very interesting. All right, let's take a look here. So let me stop the share of this. So you see what we're doing this week. It's not too bad. And we're more than halfway through the course. So that's cause for celebration. Okay. More than halfway through. All right. Okay. Oops. All right. So let's make sure this is working properly. Oh yeah, this looks good. Okay. All right. Okay. So we are now in the section where we talk about Module 9, which is statics and torque. All right. So within this module, we are chiefly concerned with if you construct a structure, all right, like even, and it could even be a human pyramid, you know, like a bunch of cheerleaders, you know, construct a structure with their bodies, you know, they get up on top of each other. And the question is, will your structure collapse, right? So here we're talking about build a structure. Will it collapse? Okay. And so in order for the thing to not collapse, you have to be in a state of equilibrium. Equilibrium. And so equilibrium basically means that the net force is zero. Okay. So you know how in Newton's second law says that F net equals ma, right? So the net force is equal to the mass times the acceleration. But if the net force is zero, then that necessarily means that the acceleration is going to have to be zero. So a system that is in equilibrium is not a system that is accelerating. And so if you construct a structure and you ensure that the net force on that structure is zero, then that structure will be in equilibrium and it will probably not collapse. Now, there's actually two types of equilibrium that we are concerned with. There are two types of equilibrium. Well, no, not that we're concerned with, but that can exist. There is something known as static equilibrium, and that's what we are concerned with. So this means that the net force is zero and the velocity is zero. Okay, so this is literally something like a human pyramid that is, you know, set up standing on the ground, and it is not moving with respect to the ground, and there's no net force. So it is not moving and it is not accelerating. The other type of equilibrium that sometimes arises is called dynamic equilibrium. So this is a case where you've got the net force equal to zero, but the velocity is not zero, okay? And so in this chapter, we are mainly concerned with this guy, right? In Module 9, we are mainly concerned with this one, okay? And so we want to know, is the structure going to collapse, right? That's what we want to know. Because collapsing is accelerating, right? You're accelerating down toward the ground, right? You are collapsing. So we want to avoid that. And so we need to attain equilibrium. Now, it is of course true that the net forces have to be zero in order for you to be in equilibrium. This is necessary, but by itself is not sufficient. for equilibrium. So this is actually known as the first condition. This is a 1. The first condition for equilibrium. All right, so this is your first condition for equilibrium. Now, there's a second condition that is also required in order for you to be in equilibrium. The other one is this. So this is known as the second condition. All right, so this is your second condition. So what does this mean? This means that, well, this is the Greek letter ta. Ta, some pronounce it tau. Ta, the Greek letter ta. This guy. This is known as the Greek letter ta. And this stands for torque. So the net torque has to be 0. So what is torque? So torque is a twisting force. So torque is a twisting force. Okay, so it is a torque that, when applied, if there's a net torque on an object, it's going to make the object begin to pivot around, right? Or spin around, right? It twists an object, right? You know, like you turn if you want to open the faucet, right? You know, so that the water comes out, you want to open the faucet, you have to apply a torque, right? You got to twist the faucet to open it so the water comes out. So that's a torque. It is a twisting force. All right. And so the second condition of equilibrium is that there is no net effect that is causing the object to twist, right? There is no net torque. Okay, so if both of these are true and the velocity is 0, then you have static equilibrium. All right. Now the thing is, though, is that even within the equilibrium, there are different types of equilibrium, right? I mean, aside from static and dynamic, even within static equilibrium, there are different types. You know, there's neutral and unstable and stable. Okay, so that's also important, but we won't get into that right now. So here, let me say a few more things about torque. So this is a twisting force. So so what does it mean? How do you define it? Basically, let's say you have a let's say you have a door. I think they give an example of a door. So you got a door like this. And so this is a door. And so over here, what we have is we've got a hinge. Over here, we have what is known as a hinge. Okay, and so what is happening is that if you apply a force, you know, if you apply a force, let's say you apply it over here like this. Okay, So you apply a force. And so what's going to happen? What's going to happen is that if you apply your force over here like this, then and this part of the door is constrained to remain attached, to the door frame, right? Because that's where the hinge is. Then the door is going to kind of want to swing open, right? It's going to want to swing open. But really, what it's doing is it's pivoting around this pivot point. It's twisting around, right? And so this force applied at this location provides a torque to the door, and it causes the door to swing open, right? It causes it to twist around this pivot point, right? So what we have is a twisting force. And how do we get it? Well, what we have to do is we have to look at this angle here. Actually, well, first we have to define what is known as the lever arm. So the distance from the pivot point where the force is applied. So this is called R, it's a vector. And so there's a displacement between the hinge and the location where the force is being applied. And there is, you can define an angle between this, which is parallel to the door, and the force. So this angle is this guy. Here, I'll draw the angle here. There's this angle. So we call this angle theta. And so the torque is found, torque is a vector quantity, by the way. So in this case, if this is the only force we have to think about, then the net torque in this particular example is going to be, actually here, I'm going to just write down the magnitude. I'm just going to write the magnitude. So that's going to be the length of this vector, right? So the distance from the pivot point that the force is being applied, and then you multiply that by the magnitude of the force, and then you times that by the sine of the angle between these two vectors. All right. And so this is the net torque, right? So this is how you define it. So anytime you apply a force that is that is distant from the center of rotation, you get a torque. And the torque produces a tendency of the object to rotate about that center of rotation, right? It's a twisting force. So now, so what are the units of torque? Well, if this is in meters and this is in newtons, so the SI unit of torque is known as the Newton meter. Okay, now please do not get this confused with joules, with energy, right? So torque isn't really energy, it's a twisting force. All right, so energy is in joules, and remember, 1 joule is equal to 1 Newton meter. Okay, but now I'm telling you that torque is also in Newton meters, but it is not energy. Okay, so this is an unfortunate thing that we have to deal with, and this can cause confusion. But usually, or I would say pretty much all the time that you're dealing with torque, the context will give you plenty of clues that we're talking about torque and we're not talking about energy. And so, it should be generally possible to keep it straight in your mind, whether we're dealing with a quantity that is in Newton meters, that is a twisting force, or whether we're dealing with energy. Okay, but just know that this exists, and it can result in confusion. Okay. Let's see. All right. And then the other thing is, so here I just wrote down the magnitude, right? And you find the magnitude by, like I said, multiply this by this by this. You get the magnitude of the torque that arises due to this force applied over this distance, right? This distance away from the pivot point. This quantity, by the way, is often referred to, this right here is referred to as the lever arm. Okay, so you may hear me use this terminology when I'm talking about this displacement from the pivot point where the force is applied. That is also known as the lever arm of the torque. Okay, so this is how you get the magnitude, but I told you it was a vector quantity. So how do you get the direction? Well, the way you get the direction is you simply say that if the direction of the twist is counterclockwise, right, as it is in this case, right, you see if the door swings open, it goes counterclockwise. So that is known as the direction of that torque is counterclockwise, which vector direction would be, into the page. And then and if it was going clockwise, that would be pointing, the vector direction would be pointing out of the page, right? So that's how you do account for the vector nature of the torque. But we, in this class, we won't be dwelling on that too much. The vector direction of the torque, will mainly be looking at the magnitude and not so much the direction. Like we won't be adding torques together, where there's an angle between them. We won't be doing that. We'll mainly be dealing with torque in one dimension, if that makes sense. Okay, so yeah, just remember for torque, clockwise equals negative torque, and then counterclockwise is positive torque. Okay, so that's how you get that. All right, so let's look at an example. Let's take a look at an example. Let's take a look at an example. All right. Okay, so I'm going to take a look at homework 6. See, we got homework 6. No, I'm sorry. Homework 9. Not 6. Homework 9, question 3. Yeah, there we go. All right, so let's take a look at homework 9, question 3. And because this is an example. This is an example. All right, so you see here we have the two children. The smaller kid is 24 kilograms, and the bigger one is 27 kilograms. And they sit balanced on the seesaw. And the pivot point is located at the center of the seesaw. All right. So if the children are separated by a distance of 2 meters, at what distance from the pivot point is the smaller child? So that the balance is maintained. All right. So let's take a look at this. This is interesting. Let's take a look here. All right. So if we go over here, and we look at, oh, actually, let's see, let's make that black. Okay, homework 9, question 3. All right. So we have the seesaw. So the seesaw is a thing that has it kind of has this, it's like a balance, right? And so the seesaw, we can imagine it's just like a uniform, plank of wood or something. And it's placed on top of what's known as a fulcrum. A fulcrum. That's what this is. This is known as a fulcrum. And so this is the place where if someone gets on the seesaw at this end, right? So here, in fact, I will draw, or no, actually, wait, let me not draw. So the seesaw itself has a mass, right? It has a mass, and so it's being pulled on by the earth. It's experiencing the force of gravity, right? Now, but gravity, remember, what gravity does to things is that it acts on the barycenter of the object. So remember when we were looking at the planets orbiting the barycenter, and then the moon was going around the earth? Well, actually, the moon wasn't really going around the earth. It was going around the Earth-Moon barycenter. And the earth itself was going around the Earth-Moon barycenter. And so everything is just orbiting this, this location in space, which is the barycenter, also known as the center of gravity of the system. So so what happens with this this piece of wood here is that if you place the fulcrum, to one side, I mean, let's suppose just for a moment that we place the fulcrum, let's say over here. Okay, just temporarily. Imagine I did that. Okay, if I place the fulcrum over here, then the barycenter of this this piece of wood is at the middle of the piece of wood, and the earth is pulling down on the barycenter. And so what ends up happening is, because the fulcrum is placed over here, this point on the plank of wood is constrained not to move, but the rest of it is allowed to move. And so when the earth pulls down on the barycenter, what ends up happening is it results in a torque. And so this piece of wood, it begins to, kind of twist around. This side goes up, this side goes down, it experiences a twisting force, right? And that's what happens when you place the fulcrum away from where the barycenter is. But if you place it at the barycenter and you just leave it alone, then the net torque is 0. You see, because the earth is pulling downward on the barycenter, but there's no displacement between the pivot point and the location where the earth's gravity is acting. There's no displacement. So that R, that lever arm, is 0, and so there's no torque due to the earth's gravity. And so if you just kind of left the seesaw like this, it would just sit there balanced, and you know, that would be static equilibrium. But what we have is we actually have these two kids on the seesaw. So we've got child number one, who's over here. We have child number one over here, and we have child number two over here. All right. And so what ends up happening is that this guy is being pulled down by planet Earth. And so this means there's a force acting downwards on this side of the seesaw equal to m1g. And on the seesaw itself, right? So the fulcrum is just the thing that provides the fixed pivot point. That's all that is. Okay, and then the seesaw itself, of course, has a certain weight, right? That's like that, but this has no effect in terms of torque because there's no distance from the fulcrum, no distance from the pivot point. All right. And then for this guy, we have M2G. Yeah. And you know, since I drew vector symbols, since I drew arrows, I should probably have vector symbols over my variables there. Okay, so these are pointing downwards like that. And so we can calculate the torque that results from this guy over here. So we can call that torque number one. So that's tau 1. And so then that's going to be R1 times M1G times the sine of theta 1. So let me label this for you here. So R1 is this distance, the distance between the barycenter of M1 and the pivot point, right? So this is the lever arm that the smaller kid is applying its torque from, and so that's this, and then over here. So what about the angle? So this is the angle, but you can see it's 90 degrees, right? So the angle between the force and this horizontal displacement is 90 degrees. So we have R1, but this guy, theta 1 equals 90 degrees, and the sine of 90 degrees is just 1. So that means that this part just becomes 1. So we have our torque that this child produces is R1 M1G. Okay. Now let's consider this torque here. Here we have torque number 2. And so for this guy, we're going from here to here. So this is R2. And so this one is looking like this, R2, M2, G. Okay, so there's our torque. And then this one also has a 90-degree angle. So again, we're just going to times this by 1 because the sine of 90 degrees is exactly 1. So we have R2, M2 times G. And so in the problem, what they tell us, they give us the distance between these two children. So the distance between these two children, it goes from here to here. Now we're going to call this D. And so R1 plus R2 is equal to D. All right. So now, if this seesaw remains balanced, that means it has static equilibrium. So that means that the sum of the torques acting on it are going to be 0. And so the only torques that really matter are the one from this and the one from this. This guy doesn't count because he has no R. So we have torque number 1 plus torque number 2 is, of course, the net torque, but that's going to be 0. And so we have, so let's see. So this one is making me twist. It's making the seesaw twist counterclockwise. So this torque is going to be positive. So this is going to be R1 M1G. And then this one's going to be negative because it's twisting clockwise. So that's going to be minus R2 M2G. And that has to add up to 0. And so now we can also use this. So here I can say that R2 equals D minus R1. All right, something like that. Okay, so R2 is D minus R1. So we have R1 M1G is equal to R2 M2G, or R1 M1G is equal to D minus R1 M2G. And we can divide both sides by G. So the G goes away. And then we can divide both sides by M2. And so we have R1 times M1 over M2 is equal to D minus R1. And so now we can add R1 to each side. So we get R1 M1 over M2 plus R1 is equal to D. So now we can factor out the R1. R1, 1 plus M1 over M2 is equal to D. And so now we can divide both sides by this quantity that we factored. So R1 is equal to D over 1 plus, here, let me see if I can squeeze this in here a little bit better. We'll squeeze it down here, D over 1 plus M1 over M2. And so this works out to, we got 2 meters divided by 1 plus, so the smaller kid is 24 kilograms, and the bigger kid was 27 kilograms. And so the kilograms cancel, we get a distance in meters, and so this works out to 1.059 meters. Okay, so that works out like that. Let's take a look and make sure that that matches. So we go over to this guy. Where did it go? Lost my window there. Oh, there it is. All right. Okay, so 1.06, right? We got 1.059, that rounds up to 1.06. So that is correct. Okay. So that is how you apply the second condition for equilibrium. You get the torques adding up to 0. All right. Okay. So what I'd like to do in the remaining time is I want to take a look at some more examples. But before we do that, I'd like to take a short 5-minute break. So we'll come back. Let's see, what time is it now? It is 10:19. All right, 10:24. We'll come back and then we'll go over the other examples. 10:24. All right, let's finish up. Let's finish up. All right, we are back. So now let us do another example. Okay, so I want to look at, I think it's problem number 6. No, this one, number 5. Okay, this is about the cheerleader who does the splits. But yeah, so this problem here, you know, I don't think it's very well constructed because it's not clear at all what exactly you're supposed to do or how it's, well, I don't know. It wasn't clear to me. Maybe it was clear to some of you, but anyway, I want to go over this one. So the gymnast is performing the split, and so in the figure below, they give information. So we must calculate the magnitude in newtons and the direction in degrees above horizontal toward the gymnast for the force exerted on each foot by the floor. Okay, so for this one, you kind of have to draw a free body diagram, but it isn't clear how you draw it, and the little illustration that they have, is kind of it's kind of misleading. Like I don't know. To me, it looked from the illustration as though the forces should be pointing horizontally, but that's not the case at all. So here, let's draw how it's supposed to be. All right. So this is homework 9, question 5. And so what we're going to do is we're going to draw the free body diagram, because that's pretty key. It's pretty key to get this right. Otherwise, there's no hope. Okay, so the center of gravity of this person is like sort of right in the pit of her stomach, right? So this is the barycenter, right? This is CG. Okay, and and so now the important thing to realize is that if we're talking about the forces all, if we're talking about the net force on the person, and there's no net torque. One way for there to be no net torque is if all of the forces acting on the person act on lines that pass through the barycenter. Okay, so that's an important point here. So let's go through the barycenter here. So we got, so the floor is pushing on the foot, on the one foot of this person, and it's producing a force that goes along the leg and into the barycenter, right into the center of gravity. So we'll call this force F, right? So that's one of the forces. And then the other one is also doing that, right? Because it's symmetric. Okay. And then, so we got these are the two forces, or actually the force, it's the same magnitude in each case. It's symmetric. It's just different directions. And then we got the weight of the cheerleader, headed down toward the ground. And so now what they draw in the picture is they have, they show that the barycenter is like this. So the barycenter, they said, is 0.3 meters above the ground. Okay, but the position of the barycenter horizontally is like this. It's 0.9 meters away from either end, right? So 0.9 meters from this foot and 0.9 meters from the other foot. All right. And so because these forces are directed like this, they're pointing right at the barycenter. you can imagine that the right triangle that you form out of one of these forces is the same right triangle that you form, that has the horizontal leg at 0.9 meters and the vertical leg at 0.3 meters. So we can think of this angle here. Actually, for right now, we'll just call it theta, right? It's the same angle on either side. Okay. And so that angle is the same angle as this one. So if I have 0.3 meters, and I have see 0.3 meters, and I have 0.9 meters. Okay. So it's the same angle. All right. Okay. So now, here, because all the forces are acting right at the barycenter, we don't have to worry about any torques because there's no lever arm, right? So lever arm is a displacement, between the is when there's displacement between where the force is acting and where the barycenter is. All right. So there's no lever arm, and so that's okay. And so what we would write is that the y components of each of these force vectors have to exactly balance the weight. So the weight only has a vertical component, and so if we take upwards as being positive and downwards as being negative, we would say that F times the sine of theta, right? So that accounts for this guy's vertical component. And then we'd add the other guy's vertical component. So that's another F times the sine of theta. Then we're going to subtract the weight of the cheerleader. So we subtract W. And so this has to amount to 0 because we are in a case of static equilibrium. Static equilibrium, equilib for short. Okay, so now I'm going to go ahead and add W to both sides. And so this, I'll combine this and turn it into twice F sine theta. So I have twice F sine theta is equal to W. And then what I'm going to do is I'm going to divide both sides by 2 sine theta. So I get F by itself. So I get F is equal to W over 2 sine theta. Okay. All right. So there's our F. This gives us the magnitude, but you can see for the magnitude, we need the angle. We need the direction. So the direction, we look here. For the angle, we look here, and we can see that the tangent of the theta is 0.3 meters divided by 0.9 meters. Okay, so that means that theta is equal to the inverse tangent of 0.3 over 0.9. Right, the meters cancel. This is a 9. The meters cancel. And so that means that you get 18.43 degrees. And so now we can take that and plug that in here. So we get F for our magnitude. So they tell us it's in very small print on the diagram, by the way. You almost can't even see it. But here I'll show you. You see in very tiny print, it says W equals 700 newtons. Okay, so that's the weight of the cheerleader. So we put the 700 newtons. So we'll put 700 newtons divided by 2 times the sine of 18.43 degrees. And so when you do that, you get 1106.8 newtons. And I think they round that to 1100. So let's see what they do there. I think they round that to 1100. Newtons. So let's see, yeah. Oh, they round it to, sorry, 1110. 3 significant figures. And then this was 18.4. Also 3 significant figures. Okay. And so then that's how you approach that one. All right. Okay, here, let me go back to this for just 1 second here. All right. So any questions about what we just went over? Okay. All right, let's do one more example. All right, let's look at number 4. Okay. So in number 4, we have a 17-meter high and a 12-meter long wall, and it's under construction. And it has bracing on it, right? So that's this piece of wood here. And so the wall is in stable equilibrium without the bracing, but it can pivot at its base. Okay, so stable equilibrium means that if you start to tip it, it'll tip back the other way. Like if you begin to tip it and let go, it'll tip back to the other way to go back to how it was, right? It has a restoring force. Unstable means the opposite, right? That you begin to tip it, and if you tip it a little bit, it wants to tip more, and until it falls over. That's unstable. And then neutral is it doesn't matter. You can adjust its position, and it doesn't experience a restoring force or a tipping force. Okay, so they want you to calculate the force exerted by each of the 10 braces. If there's a strong wind exerting a horizontal force of 786 newtons per square meter of wall, right? So this isn't really a force, this is a pressure, as we'll see later on in the course, because it's a force per unit area. It's not really a force. It's a pressure, right? Which is force per unit area. So assume that the net force from the wind acts at a height halfway up the wall, and all the braces exert equal forces parallel to their lengths. Neglect the thickness of the wall and just find the magnitude of the force. Okay. So, all right. So let's see what happens there. All right. So this is homework 9, question 4. So this is kind of similar to the one with cheerleader. So if we draw the free body diagram for the wall, what we have is we've got the wind, and we've got the bracing. So we'll call this, so this, what I'm representing here is the total force of the bracing. So it's going to be F sub B, comma, total, right? So there's 10 braces. And they've given us the force per brace. And, but what I'm drawing here is the vector for the total force. So what we have is that this is static equilibrium. So the net force is 0. And so the wind only has the x component, but this guy has both an x and a y component. And so the y component of this, isn't so important for this problem, but the y component, we can surmise that it's entirely balanced by gravity, the force of gravity on the wall. And so we don't have to worry about that. But in terms of the horizontal component, the horizontal component over here, we'll call this FBX. So this has to balance the force of the wind in order for us to have equilibrium. So we would say F wind. So again, to the right is positive, to the left is negative, minus FBX is equal to 0. And then you should be able to see that this is a right triangle that I have. So then this guy is going to be this force times the sine of the angle. So what we have is we've got, so based on this, we have we have FBX is equal to F wind. And so that's going to equal FB total times the sine of theta. And so FB total is equal to F wind divided by the sine of theta. And but what they want us to find is they want us to find FB single. They want us to find the force per brace. And there's 10 braces. So we have to take FB total and divide it by 10. So that's going to be FB total divided by 10. So that's going to be F wind divided by 10 times the sine of theta. And so now, but what is F wind? So F wind is equal to the area of the wall times the wind pressure. And the wind pressure they gave us, they said it was 786 newtons per square meter. All right. And so that is equal to the height of the wall times the length of the wall. Yeah, let me draw this a little better. The height of the wall times the length of the wall times the pressure. And so what we end up with is we get FB for a single brace is going to be the height of the wall times the length of the wall times the wind pressure divided by 10 times the sine of the angle. And so that is equal to 17 meters times 12 meters times 786 newtons per square meter divided by 10 times the sine of 35 degrees, right? 35 is what they give us for the angle. It's in the picture. And so this works out to, so we got square meters, meters, meters. So it's in newtons, which is what we want. So that works out to 2,709.55 newtons. And so what they do is they round that up to 2.8 times 10 to the 4 newtons in the actual solution. So here, let's take a quick look at that. Okay, so you see what they do to three significant figures is they put 2.80 times 10 to the 4, which is what my answer rounds to. Okay. All right. So I think that's about all we have time for. So I'll just put this back up. And then, I think that's about it. So the next time I will see you, it would be next week, because we don't have our Zoom session and we don't have our lab session on Thursday. So I hope everyone has a good weekend.
Thank you, Professor.
Thank you.
Have a nice weekend.
Thank you.
Thanks, you too.